How do microprocessors drive the digital world so quickly? Imagine a tiny chip inside your phone or computer that can perform billions of calculations every second. That's what a microprocessor does, and it's the engine behind all our digital technology. But how does it work so fast? Let's break it down into simple parts. Microprocessors are built with special design features that make them perform at incredible speeds. One key idea is the Harvard architecture, which uses separate pathways for instructions and data. This means the processor can fetch instructions and access data at the same time, doubling the speed compared to older designs that use just one pathway. Another trick is pipelining. Think of it like an assembly line where different steps of processing happen at once. While one instruction is being executed, the next one is being decoded, and another is being fetched. This overlapping process allows the processor to handle many instructions in a single clock cycle, making everything run much faster. Modern microprocessors also include multiply accumulate units. These are special hardware parts that can multiply to numbers and add the result to an accumulator in just one clock cycle. This is super useful for tasks like audio and image processing, where lots of math happens repeatedly. Many processors have two of these units, so they can do to multiply and accumulate operations at once, speeding up complex calculations. Memory design plays a big role in speed too. Processors use multi-level caches that store frequently used data close to the core. This way, the processor doesn't have to go all the way to the main memory every time it needs data. It also uses preloading techniques to guess what data will be needed next, so it's ready when required. Direct memory access controllers also help by moving data between memory and peripherals without bothering the processor, so it can keep working smoothly. The way the processor generates memory addresses is important as well. Special address generation units can calculate addresses in parallel with other tasks. Features like circular and bit-reversed addressing help speed up algorithms that need specific data patterns, such as fast Fourier transforms used in signal processing. Clock frequency, measured in gigahertz, is what most people think of when they consider speed. Higher frequency means more clock cycles per second, which can lead to faster processing. But it's not the only factor. A processor with a lower clock speed but better architecture can outperform a faster one because it does more work per cycle. Instruction set design also helps speed things up. Some processors have special instructions that perform common tasks in fewer clock cycles. Vector instructions allow one operation to process multiple data points at once, boosting throughput. Bit shift and other specialized arithmetic instructions reduce the number of steps needed for calculations. Power efficiency and thermal management are vital too. If a processor wastes less energy as heat, it can run at higher speeds without overheating. Advances in semiconductor manufacturing make transistors switch faster while using less power, helping processors become both faster and more energy efficient over time. All these features work together seamlessly. A microprocessor with fast memory access, effective pipelining, specialized units, and smart instruction sets can perform billions of operations every second. This is how they handle real-time signals, complex algorithms, and massive data streams. It's a mix of clever design and engineering that makes the digital world move so quickly.